Hello students, this is the recording for the 4I lesson on refraction. Alright, so let's go ahead and take a moment to pause the video and try to match these up on your own, and then we'll go over the answers. Alright, so taking a look here, you have absorption, reflection, refraction, and transmission of light. So we want to think about what all of these things mean. So remember that when you think of the word absorption, you should think of the word absorb, obviously. Alright, and so this is going to be when light gets absorbed or goes into a type of matter and gets converted to a different type of energy. So right here, specifically, when you absorb light, it generally turns into heat, right? Which is why, for example, black shirts absorb a lot of light and they get much hotter in the summer than a white shirt, which does not absorb as much of the light. All right, let's go ahead and take a look at reflection. Reflection, think about how when you look in a mirror, you're looking at yourself kind of bounced back towards you. So that should be pretty obvious. This one is going to be when light bounces off of matter right here. Refraction is kind of a newer one probably, but refraction is a little bit different than reflection. Reflection is when something bounces right back at you. Refraction, on the other hand, is just when it bends. So it's not going to come back towards you, but it is going to bend as it passes through matter. Again, this has to do with what we talked about in our previous lesson. This leads to things like rainbows. All right, let's go ahead and talk about transmission then. Transmission means that all of the light is transmitted, meaning it goes through the matter. So that would be this one right here. Again, make sure that you understand that. If you don't, make sure you go back and review that. All right, so this is our answers right here. Let's go ahead and take a look at our schedule. There are only 11 days left of the school year and then courses are over. No assignments will be accepted after that final deadline, which we'll go over in just a few moments. We are wrapping up Unit 4 today by talking about refraction, and then you will have a couple lessons on Unit 5, and next week you will have your last exam, your only exam, but you'll have an exam on Units 4 and 5. So again, we're wrapping up today talking about waves by looking at refraction. Don't forget that the last STAR 360 assessments are this week for all students. They are worth 5% of your grade in every single class, not just your English and math classes, but also science, history, PE, tech, careers, etc., etc. So for reading, that will be tomorrow on Tuesday, May 25th, during whatever your normal period 2 class is, and then Wednesday during whatever your normal period 3 class is for math. Remember, we did originally have an exam planned for this Tuesday, but to prevent the exam falling on the same day as STAR 360, we just kind of combined it. So we are going straight from 4I Unit 4 to 5A Unit 5, and then we will have a combined Unit 4-5 exam on this Wednesday. Don't forget that this is when it's due. However, it'll be zeroed out on Thursday, so you do have a bit of a grace period, end of the day on Thursday. And so then, so you kind of have 2 days to do it, even though it's technically due on Wednesday. And then don't forget that after that, you have a week to make up any missing work. You should be focusing on projects and exams, since these are worth 70% of your grade. And it is literally impossible to pass without them. Okay? So again, that is your last day here is on June 9th. Remember that courses close at 11:59 p.m., so make sure everything is turned in before then. There are no extensions, and tech issues will not be excused on the last day. So if you say, I don't have access to my computer, or my computer shut off at 11 o'clock, or the course crashed at 11:30, not something we can solve. All right, so if you wait until the last day, that's not something we can fix. So please don't wait till the last minute. There will be no extensions past 11:59 on this last day, because there's a very fast turnaround for grades and for graduates, so no extensions. All right, so at this point, I am now on maternity leave, so if you were on my roster, you are now working with Miss Smith. However, if you do need help on any of the actual assignments, please contact Mr. Bangle, just because Mr. Bangle has a science background and is specifically has been with us all trimester, and so he knows the most about all of the projects and everything. So please make sure you contact him if you need help on anything. All right, so today we're going to take a look at defining refraction, providing examples of refraction, and explaining specifically one good example of how refraction can be used when correcting vision. So I wear glasses. I'm sure some of you wear glasses or contacts, and we'll talk about how refraction is related to those things. So at this point, if you haven't already, please make sure that you open up your 4i notes. You can go to your grades tab. Everything is in your grades tab. Go ahead and open that up and then go ahead and click Start Quiz to get it started. All right, so what we're going to go ahead and do is we're going to watch a quick video, and the question is, where did the penny go? So you're going to go ahead and make some observations and see what do you notice happening here.
For this experiment, you're going to need a glass, a penny, and a jug of water. It's a really quick and easy experiment to do. You simply put the penny on top of a tabletop and put the glass on top of the penny. As you can see, the penny is right underneath the glass. But as you pour the water in, the penny seems to disappear. Look closely. Where is it?
All right, so you should have been able to see there that this is really interesting, that again, the penny is still actually there, but we can no longer see it. So today we're going to be talking about why can we no longer see the penny. Let's go ahead and see kind of what they are talking about here.
The penny is still underneath the glass. But what's happened here is that something called refraction is happening. Refraction is when the direction of light rays is changed by a substance, in this case water. As light rays pass through the water, they slightly change direction, meaning that you can't see the same thing as you could before, which in this case means that the penny looks like it's disappearing. Isn't that brilliant?
Yeah, so something I find really cool here is that if you take a look at when he's filling up the cup here the second time, he kind of fills it up a little bit more slowly. And what you'll notice is that you can actually still see part of the penny through the surface of the water for a little bit before it disappears. And again, that's just because light is bending, but it's going to bend differently from above the water versus from below the water. So you can actually see the penny in the wrong spot for a little bit until finally it's so full that you can no longer see the penny. All right, so let's take a look here. Things that he talked about here. The penny, again, is still actually there. However, as we add water to the cup, light begins to bend within that water. And so bending or refracting means that now the light is hitting the penny differently. And so we can no longer see it the same way that we could before. All right, so let's go ahead and talk a little bit about this. So again, we're talking about refraction mainly today. We already kind of learned that refraction is when light bends, but we'll talk about specifically how does this work with a lot of visual or optical meaning like eyes, phenomena that we see. So for example, the main one that we're going to be talking about today is that when we go from water to air or air to water, light changes direction. So it bends again, and that's going to be responsible for a lot of things that we see. So one of the examples we'll talk about is fish. All right, this is going to go ahead and be number 2. Go ahead and fill in the blank with the word bends, only the word bends. Make sure you pause the video and continue playing when you're ready. All right, so let's go ahead and talk a little bit about this. So this is why it's so hard to catch fish when you are above the waterline. So if you've ever tried to catch a fish or catch anything underwater, but you are above the water, you'll know that it's actually really hard to do because everything looks like it's in a different spot than it really is. So what you can see here, for example, is that this is what we see where the fish is, but in reality the fish is actually a little bit lower and more toward and closer to you. So this is important to understand if you're ever spear fishing for some reason, that you should actually aim a little bit underneath the fish because of how light bends. So let's go ahead and talk about how this happens. So remember that light hits objects and then comes off of objects. That's how we can see things, right? Is as light bounces off of objects, that's how we can see things. So what that happens here is light starts at the fish, right? So light is bouncing off of the fish. And as it bounces off the fish, it then goes up through the water. And you can see here that it goes up through the water through this kind of yellow line right here. Okay. The problem is that once that light hits the air, again, it bends. And it bends this direction. So you can see that it bends a little bit flatter. And the problem is that once that light ray now hits your eye assumes that the bent part is true. All right, so it bends and hits your eyes, and then as you're looking at it, your brain assumes that the light, the way that it's traveling in the air, is in fact the correct direction. And so your brain makes the assumption that, all right, the light's bending to hit my eye like this, and so therefore I just extrapolate that, and I think, oh, that must be a straight line, and therefore I see this weird image that's actually above where the fish really is. So your brain assumes that the light that you see in the air is the correct direction, whereas reality, right, that's not true because light bends in water, but since we're not under the water, we don't notice that, we can't observe that. And so the result is that the image is in the wrong place. A lot like with our penny, we saw that the penny was still kind of there, but it was kind of above where it was for a little bit before it completely disappeared. This is going to be number 3, so again, your brain assumes that the light in the air is correct. So go ahead and fill in the blank with the word assumes, only the word assumes. Make sure you pause the video and continue playing when you're ready. All right, so this again is also why the penny trick works, okay? So this is why the penny actually disappears from the bottom. So again, we always start at the object, not your eye, but you actually start at the object. So again, light is coming off of the penny. That's why you can see the penny in the first place. So light is coming off of the penny right here, okay? And again, it's going up, up, up through the water. But the problem is, again, once it hits the air, it begins to bend flatter. So it bends flatter and continues to your eye. But again, your eye and your brain are not that great at figuring out what's going on. So your brain explodes and your brain assumes that the direction of the light in the air is the true direction. So your brain thinks that, oh, this bent ray right here is really what's happening. And so your brain then makes an assumption and extrapolates further. It goes back and it says, okay, that must be where the penny is right here. Okay, so again, we saw that penny kind of moved higher and higher in the water until at some point it disappeared just because of how the glass was shaped. But again, so we can see that we assume the penny is higher than it really is, and that is eventually why it disappeared from the bottom. Okay, so it's not in the right spot. Your brain interprets that and puts it in the wrong spot. Okay, let's go ahead and talk about another example. So far we talked about the fish example. We kind of debriefed the coin example. We can also take a look here. What do you notice about this chopstick here? All right, so I'm going to go ahead and put that up for you. All right, so notice here, let me actually get a piece of paper to kind of block out the background here. All right, so what do you notice about this chopstick? Right, so what you should notice is that the part underwater actually looks like it's kind of broken from the part above the water. And again, this is a great example of refraction and probably something that you've observed throughout your life. So what you will notice is that the pencil appears to be broken. Now the reason why, again, is because light is bouncing off the part that's under the water, but that light that bounces off the pencil underwater then changes position once it hits the air. Right, so we can see that right here, that we have the light right here bouncing off of the pencil. It goes into the air, and at that point it bends. But once it bends, sorry, let me clear that up again. But once it bends, right, so it's bending right here. Once it bends, your brain then assumes that that bending is true. All right, so your brain assumes that that bending is true, and so it extrapolates back. And the result is that your pencil appears to be too high. So the pencil, the part bouncing off, the water underneath, it appears to be too high. On the other hand, your brain right here sees the pencil as it is because the pencil and your eye are in the same environment. And so this part does not appear to bend. So the result is we end up with the part underwater looking like it's bent, whereas the part above water looks normal. And so that is why your pencil appears broken. So another cool example of refraction, this time though with two different parts, one being refracted, the other one not. All right, another cool example is rainbows. We kind of talked a little bit about this, but we're going to talk a little bit further. We kind of used a prism to show the different colors of the rainbow, but today we'll actually talk about how real rainbows are formed. So how real rainbows are formed, you need light and you need water. Okay, so when white light being the light that we get naturally from the sun, when that hits a water droplet, the light begins to refract or bend. So you can see that right here. We have white light coming in from the sunlight. It hits the water droplet and bam, it begins to bend. Now we saw on our previous lesson that when light bends, remember that the different colors of light bend at different rates, right? So red light bends the least, the reason being because it's the longest wavelength, and so it interacts the least with the water, okay? The violet light, on the other hand, has the shortest wavelength, and so the result is it has to cross that material a whole bunch, that water a whole bunch. And so it interacts with the water the most, and so it slows down the most and bends the most. So you can see our red light stays much less bent, right? It stays at the top, whereas the purple light is much more bent and goes towards the bottom. Now, not only do we have refraction here, but we actually also have reflection, because when we have droplets, droplets are spherical, and so the refraction here is going to then become reflection. So we have light coming in, it refracts or bends, and then it actually reflects off of the back of the water droplet. And at that point, it's going to go ahead and come out of the water droplet, and when it comes out, it refracts again. So we can see here that we end up with the light being very, very separated after all of these steps. So it refracts again, and now we get very distinct colors of red, orange, yellow, green, blue, and violet. All right, so that is also how a rainbow forms. Again, the start, the middle, and the end that you can see here. This is going to be number 4. Again, when white light refracts, it refracts the colors differently and they separate because of how fast those different colors travel within the water. Go ahead, pause the video and fill in number 4 with the word separate, only the word separate, and continue playing when you're ready. All right, so let's go ahead and talk a little bit about our last application here, which is lenses. So a lens, like in your glasses or in a contact, these ones also refract light. And we can actually take advantage of this to help correct vision. So let's go ahead and talk a little bit about the 2 different types of lenses. So first off, there are concave lenses, which if you think about concave, it literally looks like the word cave. And so you should think that it's like curving inwards, right? Like how a cave curves inwards into a rock formation. All right, so you can go into a cave, right? So the surface is going to curve inwards, and you can see that right here. So this literally looks like a cave, right? Looks like a cave, okay? And so the result is here. Actually, sorry, I apologize. This one is actually going the other direction. Here we go. And let me flip that. All right, so this one looks like a cave. Good. All right, and what you'll notice here is that as the light goes towards here, right, so for a while the light is straight. As it hits that concave surface, though, it begins to spread out or diverge, right? So spreading out is called diverging, and so the beam of light spreads out, diverges, okay? Convex, on the other hand, is going to be the opposite. So convex, VEX, is when instead the surface curves outwards. All right, so again, we can see light coming in straight here. This time the light's going to the right. And we have a convex surface, which curves outwards here towards the light. And the result is that as that passes through, we end up with a beam of light that converges or comes to a point. And that point right there is called the focal point. And that is going to be right there. Okay, so let's go ahead and talk a little bit about how this helps us. First, go ahead and fill in the first blank for number 5 with inwards, the second blank with the word outwards. Don't forget those last S's. Remember that capitalization does not matter, but spelling does. Take a few moments, pause the video, continue playing when you're ready. All right, so let's talk a little bit about how your vision works. So the whole point of your eye is trying to focus light onto what is called the retina. The retina is the back of your eye, and these are neural tissues, meaning like brain and nervous tissues that can sense light. All right, so again, it's very important your brain and your body is able to interpret light in a specific way so that your brain can actually understand it. All right, so you can see right here, here is our retina. Okay, so we need to get light to this retina. So normally what happens in a healthy eye is that we have light go through the cornea, which is going to be kind of the front of your eye right here. So you can see this is where we're starting. And then you have a lens right behind that cornea, which is right here. So you can see that. Right, so you have a lens behind here. And that lens is like, it's actually like fairly thick and stuff. I did a dissection on a cow's eye when I was in junior high. And the cornea, the lens is like, it's like thick and disc-like. It literally looks like a lens. It's a very odd feeling too. But what happens is that lens can adjust. So the lens can open, close, change shape here. And what it does is that it's going to adjust the light coming in through the cornea. All right, so we have our start and then our middle. So the lens is going to focus that, is going to adjust that light. And the whole idea is that that lens, which we can see is convex, it curves outwards, means that we have a focal point here. All right, so anytime we have a curving outwards, sorry, let me draw it like this. Anytime we have light coming in and hitting a surface that is curved outwards, okay, then it's going to converge to a focal point. So we can see that focal point, and the whole idea is to get that focal point to hit the back of the retina. Once that focal point hits the back of the retina, you then have an optic nerve connected to the retina, and the optic nerve, or optic meaning eye, then can take that image and send it to your brain in order to interpret. So your brain's pretty amazing. All right, but again, if for some reason you cannot get your eye to adjust this focal point to actually hit your retina, then you have a big problem, and that is where vision problems come in. All right, so we can go ahead and fix those though. Not all vision problems, but a lot of vision problems we can fix every day. Everyday problems with artificial lenses. So artificial lenses or corrective lenses change the index of refraction. They change how much the light bends. And that what that means is they're literally moving the focal point so that it hits the retina. Again, we're trying to get the light to hit the retina, okay? Now, if you are nearsighted, that means that you can see things that are close to you, but that everything far away is blurry. So you can see here a picture of a nearsighted eye. So nearsighted eye, the retina, the focal point is not reaching the back of your retina. That's why, like if you're close enough to something, right, your eye can adjust enough for that and make it hit the back of your retina. But as things get further and further away, your eye can no longer compensate. And so the farther away things get, the less and less your focal point can hit your retina. All right, so far away things are blurry because your eye cannot keep up with the distance, and your lens cannot make your focal point reach the retina. Okay, so it's just getting too far away. All right, so let's go ahead and talk a little bit about what we can do then. So what we can do is we can use a concave lens, right? Concave right here, meaning it looks like a cave, so the light comes into a cave, okay? And we learned that concave lenses cause light to spread out more or to diverge. Now, it's not causing it to diverge as much as what we saw in the first image where it completely diverged. Instead, it's just causing it to diverge a little bit more so that your focal point can stay open a little bit longer, right? So it spreads out your focal point a little bit more, or spreads out that light a little bit more so that the focal point doesn't come to a point quite as quickly, right? So that means that we can actually reach, let me get a different color here. We can actually reach further back. And so now your focal point is actually reaching your retina, the back of your eye, and you'll get a clear image, right? So again, we're not diverging to the point where the light is completely like this. It's just that here's where my focal point usually is. And so by diverging the light a little bit more, we're able to make that focal point go back a little bit further, right? We're stretching out that focal point so that it reaches our retina. Now, on the other hand, if you are farsighted, all right, so farsighted means that when you have things far away, your focal point in retina can accommodate that. However, as things get too close, your lens is still trying to look at things far away. So what we can see here is that this time your lens cannot adjust things that are close up. So it still thinks that things are further away than they actually are, and so it's adjusting too much, and so it's going back too far. So you can see here that the the focal point, the lens is adjusting, the focal point is going past the retina this time. So everything close up is now blurry. All right, when you're far enough away, it's not a big deal because, again, your eye is really good at reaching far back. But as you get closer, your eye is so good at reaching far back that everything close up now seems blurry. Okay? So this time we're going to use a convex lens. And again, a convex lens means that as the light comes in, it's hitting a it's curving towards it, right? So here's the light, and this time it's actually curving towards it. Okay, so a convex lens is going to converge things faster, right? So we saw concave spreads things out. Convex, though, makes things converge even faster. So what happens here is it's going to converge that light a little bit faster than what your eye can normally do. And so the result is it shortens the light's distance to the retina. All right, so now you can see that we have a much better result here where it's actually hitting the retina just like it's supposed to be hitting, right? So it's converging it just a little bit faster so that it actually reaches so that it does not reach past your retina. All right. Cool. So this is going to be the answers to number 6 and number 7. Number 6, fill in the blank with the word further. Spelling matters. Capitalization does not. Number 7, go ahead and fill in the blank with the word shortens. Concave lens diverges, spreads it out so it can go further. Convex lens converges, shortens it. All right, go ahead and pause the video and continue playing when you're ready. All right, so the last question here you need to complete on your own. I've said this 1,000 times at this point. What is the purpose of the eye? To focus the light onto which part? Are we focusing it onto the lens in the front? Are we focusing it onto the retina in the back, the cornea in the front, or the pupil, which is between the lens and the cornea? Go ahead and pause the video and continue playing when you're ready. All right, so we talked about refraction, examples of refraction in rainbows, the pencil, the broken pencil, fishing, as well as our penny trick. And then we also talked about how refraction can then be used in a very practical way to correct vision. Go ahead and reflect to yourself. How do you feel about today's objectives? If you feel like you are over here on the very confused or still need some help side, please make sure that you are contacting Mr. Bangle. Again, Mr. Bangle is going to be our science guru here, so make sure that if you need help on projects later on the exam, or if you need help just understanding concepts, that you reach out to Mr. Bangle and get some individual tutoring. If you're feeling pretty good or awesome, though, that's great to hear. Hopefully you'll do well on the exam in just a few days. All right, so make sure you submit your 4i notes, and we will see you later. Thank you so much.